Hello and welcome to this video. This is the second video in the series of the electrostatics videos for class 12 actually. In this video we shall talk about the Coulomb's law. The entire electrostatics, there are only two experimental laws, experimental inputs actually. One of them is the Coulomb's law and the other is the principle of superposition. We'll take a look at both of these in this particular video. Okay. Now, this Coulomb's law, this talks about the force of interaction which is there between two charges. This law was given in 1785 by the French physicist Charles Augustin de Coulomb. And this law governs the electrical force between a pair of point-like charges. Now, what the law says, basically what Coulomb was able to find out is that the magnitude F of the electrostatic force between a pair of point charges, which we're going to call as Q1 and Q2, which are kept at distance small r from each other, or just r from each other, is found to be directly proportional to the product of the magnitudes of the charges, that is, F is proportional to Q1, mod Q1 into mod Q2, and it was found to be inversely proportional to the square of the distance between them, that is, F is inversely proportional to r square, or F is directly proportional to 1 by r square actually. So if I combine these two, or if we just combine these two facts, the result is that the force varies as the product of the charges and inversely as the distance squared, that is, F is proportional to mod of Q1 into Q2 by r square. In this case, I have simply replaced this product of these two charges magnitude by the corresponding modulus of the product over there. They are identical in any case. Fine. So this is what the Coulomb's law is. Interestingly, Coulomb was able to derive this variation without actually knowing what the magnitude of charges were there actually. First of all, he used a particular device which is referred to as the torsional balance, which was earlier used by Lord Cavendish to measure the universal gravitation constant value, which appears in Newton's laws of gravitation actually. What he was able to do was to charge two spheres, and without knowing what the charges are actually present, he first fixed the distance between the two spheres and then keep on varying the distance between them, and fix the two charges and vary the distance. So by doing that, he was able to derive as 1 by r square variation. Now for finding out the fact that the force actually dependent on the product of the charges, what he actually did was, he didn't know still the magnitude of the charges actually. So what he did was, he used the fact that when we have a metallic conductor, and if I just touch, say this is having some charge Q, we shall later on see that when we charge a metallic conductor, the charge stays on the surface actually. So if it is now brought in contact with another identical sphere, if I just touch them for example, then the charge is going to divide on each of them equally. So each of them is going to become Q by 2, Q by 2. Fine. So what he did was, he used this particular idea. He considered two charged spheres, find out the force between them, measure the force between them, then he divided the charge of both the spheres, and then again find out the product. Again find out the force actually. So by doing this, we were actually able to reduce this particular dependency, that force was proportional to the product of the two charges. Now in this case, the constant of proportionality is written down as 1 by 4 pi epsilon naught, where epsilon naught is referred to as the permittivity of free space, which appears in relation to the optical density of the substance. This constant epsilon 0, the permittivity of free space, it has a value which is around 8.85 into 10 power minus 12 farad per meter, constant in this non-simple way, so that some other relations become much more simpler because they are more used often actually. Now for all practical purposes, we can actually take the value of 1 by 4 pi epsilon naught to be equal to 9 into 10 power 9 Newton meter square per, well it should have been kg square, no sorry, Coulomb square actually, because this is looking at the charges. Okay, so that was a mistake. This becomes, as a result of which we can combine all these things and ultimately write down the Coulomb's law in this particular form. F is equal to 1 by 4 pi epsilon 0 into mod of q1 q2 by r square. Now what if I have more than two charges? In that case, what will be the way to find out the forces between them? So as it turns out in this case, okay, before that, there are a few remarks actually regarding this Coulomb's law. First of all, we notice that Coulomb's law is applicable for point-like charges only, okay, or it also acts between uniformly charged spheres, but it will not work, for example, if I have two cubes and we try to figure out the distance, the force between them by using this Coulomb's law. It will not work because, it will work, for example, if you keep them very, very far apart, but it won't work if they are close enough and they are not point charges or they are not spheres, uniformly charged spheres. Okay. Second is the fact that the force between them, the charges, is attractive if they are of opposite sign and is repulsive if they are of the same sign. This is already a known fact. Already looked at that in the last video actually. The next property that we should keep in mind is the fact that the force between the charges, it acts along the line joining the center of the charges, or if they are spheres, in center of the spheres. This is actually a property of something called a central force, and that makes the Coulomb force also a central force. And you should also notice that the Coulomb's force rather, it actually follows Newton's third law, which means that the force which Q1 exerts on Q2 will be equal and opposite to the force which Q2 exerts on Q1. Okay. Now, if we consider, because the Coulomb's law deals with force and force is a vector quantity, so it's useful to write down the Coulomb's law in a vector form. That in this case can be done if we take up the position vector of the second charge Q2 with respect to Q1 and call it as R21. So that is basically giving us the position vector of the second charge with respect to the first one. Then if I look at the force which Q2 experiences because of Q1, which I am going to call as F21, that is force on Q2 due to Q1. Assuming that these two charges are both positive, this force is going to be repulsive. So this force, which is F21, is actually pointing away from Q2, so it's pointing in the direction of the vector R21. As a result of which, we could write down F21 as 1 by 4 pi epsilon 0 Q1 Q2, in this time there is no mod by the way, divided by mod R21 whole square, that's a distance squared, and then the direction is going to be along the direction of R21 vector, so there is a unit vector along R21, that is R21 cap. By using the fact that any kind of a unit vector is nothing but the vector divided by its own magnitude, we can use this fact and write down the vector R21, that is vector R21 divided by mod of R21 cube, because one of the modulus was coming from this unit vector that gets absorbed into the power, as a result of which we end up getting, in this case, mod of R21 cube over there. Fine. This is a vector form, and you should notice in this case that over here Q1 and Q2 represent the charges together with a sign. So these are algebraic numbers in this case. So if there is a negative charge, we will have to consider a negative sign as well. Okay. Fine. Now, as I was saying, if I wanted to find out, or if we have more than 2 charges, so for example 3 charges or 4 charges for instance, then how do I find out the force which any one of them experience because the others? This is the is given by, or this particular force calculation is basically facilitated by this principle of superposition, which is again experimental law, not a logical necessity. And this tells us how to find the net force on one of the charges due to all the other charges which are present. There are 2 things. First of all, what this result says is that if we have, first of all, look at any pair of charges, the force between them does not depend on the presence of the other charges. That's one of the part. So for example, if I have Q1, Q2 and Q3, then the force which is there between Q1 and Q2, in the presence of Q3, it will be the same force which Q1 and Q2 were exerting on each other in the absence of Q3 as well. So whether Q3 is present or not present, the force between Q1 and Q2 remain the same. So this is one thing. The other thing therefore is, if I wanted to find out the net force on, say for example, a charge Q due to the other charges Q1, Q2, Q3 and so on till Qn, then we can obtain this by vectorically adding the forces exerted by each of those other charges on Q. Okay. So mathematically we could write down that the net force on Q, one charge over here, is the sum, the vector sum of the force on Q due to Q1 plus the force on Q due to Q2 and so on. So basically what I need to do is I need to find out the force which the individual charges exert on Q had the other charges not been there, and then add all of them in a vectorical manner, taking the directions into account as well. Okay. This principle of superposition also allows us to find out the force between extended charge bodies. We could basically apply the principle of superposition and some integration to find out the force, for example, which is exerted by a rod of charge and on a point charge, for example. We shall see some examples over there. So let us say we just work out some examples. We consider a few examples of the force calculation. First of all, we have to find out the force which exists between 2 protons in the nucleus of atom. Okay, remember that protons are inside the nucleus of an atom. Assuming a separation of 4 into 10 power minus 15 meters. So this is going to be simply obtained by using the Coulomb's law. The force expression is 1 by 4 pi epsilon naught into Q1 Q2 in modulus by distance square. Now in this case, if you work in SI unit, the result will be in SI unit. So 9 10 power 9 into, because both of them are protons, the charges are identical. So we have 1.6 into 10 power minus 19 Coulomb whole square divided by the distance, which is 4 into 10 to the power minus 15 meter whole square. So in this case, if we just do the computation, we have got 9 into 10 power 9 and then 1.6 upon 4. We can just take everything inside the square. So I get 0.4 upon the division, and then 10 power minus 19 and minus 15 denominator, so I am going to subtract. that will give us 10 power minus 4 upon, and then square it. So that makes it 9 into 10 power 9 into 0.16 multiplied with 10 power minus 8, and 10 power 9, 10 power minus 8 combines gives 10 power 1, which is 10 over there. So that 10 I multiply with 0.16 to get 1.6, and finally we multiply 9 and 1.6. That gives 14.4 Newton. Okay, so that is a force which two protons exert on each other inside the nucleus. This might seem like not a very large force over there, almost the weight of 1 kg block, approximately 1.5 kg. However, this is quite a large force, a huge force in fact, for the proton. If you see the mass of the proton, that's of the order of 10 power minus 27 kg. So this force can produce a huge amount of acceleration. So you could see that this extreme or this very large Coulombic repulsion must be balanced by something else, and that something else turns out to be the nuclear force among the proton. Okay. Okay, as another example, let us try to work out the force between, not between, but on the charge Q3 over here, because of the other two charges Q1 and Q2. We find that Q1 and Q3 both are 5 microcoulomb, while Q2 is minus 2 microcoulomb. So in order to find out the force, net force on Q3, we first of all find out the force on Q3 because of Q1. Now because Q1 and Q3 both are positive, so they will repel each other along this line. So one of the force acts this way, a repulsion. On the other hand, the charge Q2 is negative, so it will attract Q3, and as a result of which there is one more force this way. Let us call this force as F2 and the other force as F1. You notice that because this is a isosceles right triangle, this angle over here is nothing but 45 degrees. As a result of which you could add these two forces, F1, F2. You could definitely add them vectorically. You can find the modulus by using the formula to find out the magnitude of the sum of two vectors. However, it's much useful in this case to find out the force by projection along two directions. But before that, we compute F2 and F1 individually. So F1, which is the force between both the 5 microcoulomb charges, that will become 1 by 4 pi epsilon 0 into 5 into 10 power minus 6, that's for micro, because the two charges are identical, so you get square, divided by the distance. The distance between them is √2a whole square. And that becomes 9 into 10 to the power 9. Then you have 25 into 10 to the power minus 12 divided by 2 times of a square. A in this case is 0.1 meter, 10 power minus 1 basically. So this square becomes 10 to the power minus 2. So that if I simplify them, we have got 25 into 9 is 225 already. So we get this upon 2 into 10 raised power. I have minus 2 going up, becoming 10 to the minus 10 into 10 power 9 becomes 10 power minus 1. And that gives us therefore, so this one turns out to be about 11.2 Newton if I round it up to 1 decimal place. Next we obtain the value of F2. So the force F2 can be obtained by, in this case, using the similar formula. I get 9 10 power 9 into the charges in this case are different. One is 2, one is 5 microcoulomb. I do not use the sign right now. I already know they are attractive in nature. So I get 2 into 10 power minus 6 and 5 into 10 power minus 6 divided by the distance is 0.1 square. That becomes 9 into, we see we have got 10 in the numerator, 10 power minus 12 and denominator is 10 power minus 2. So if I say there is 10 power 9 as well, that was present. So if I consider this 10 comes out by multiplying 2 and 5 actually. So what we have over there is 9 into, we have got basically 9 Newton. This is 9 Newton. And now we could obtain the force between them, or the net force on the charge Q3 as the resultant of these two forces. It is useful to find out the resultant by breaking up the force F1 into two components. One will be the horizontal component, which I could consider as F1 into cos 45 degrees. The other one is the vertical component, which is F1 into sine 45 degrees. Now once we have this, I could find out the net horizontal force in this diagram, turning out to be towards the right if I consider, well, it will be towards the left. So towards the left if I consider, I get F2 minus F1 by root 2, which is what cos 45 degree is. F2 is 9 Newton and F1, which is 11.2 divided by root 2. 1 by root 2 is roughly 0.7. So I have got 9 minus 0.7 times 11.2, giving us 9 minus 7.84, which gives around 2.16 Newton, while the vertical force is simply F1 sine 45 degree, which is F1 upon root 2, which is 7.84 Newton. As a result of which, if I square and add them up, I get the resultant force. Fine. That I just leave it to you finish up. This was a couple of examples how to apply the Coulomb's law. We shall be looking at some more examples during the live sessions. So thank you for your attention and see you in the next video where we introduce the electric field. Okay, thank you.